with the schedule.
Radhakrishna, I think the chat will only be visible to Zoom, so you may want to ask the question to the speaker so that people on the portal can also hear the answer. Just quickly go over the questions.
Okay, so one of the questions is, how do you monetize your patents? Tons of patents are filed, but few of them get into standards.
Thanks, Ganti, for the introduction. So let me share my screen. I hope you can see the screen and I'm audible. Yeah.
Yes.
Okay. Good morning, everyone. In today's talk, I'm going to talk to you about some of the research we've been doing on the 5G core. Okay, so to give some background about myself and this work, so my team has been part of the end-to-end 5G testbed project funded by DOT, and as part of this project, the teams at IIT Bombay, CIVIT, and IIT Madras together, we've developed a fully standards compliant 5G core, right? And my students and I, we are using this core in order to work on some research problems around how to improve the performance and fault tolerance of the 5G core. So there are some open source versions available, but they are not really amenable to this kind of research. So in my talk, I'm going to talk about a couple of research ideas that we have recently published, and also a few other areas that I'm going to talk about. And all of these are improvements that we see to the 5G core. And this can translate into newer ideas to start our discussion on 6G core. And I'm very grateful to the entire 5G testbed team, as well as my PhD and master students who've helped me come up with some of the research and ideas in these slides. So for those of you who are familiar with what is the 5G core, here is a brief introduction. So the 5G core is the entity that connects external networks to the wireless RAN, right? So you have the user, you have the radio access network, and you have external networks. So the 5G core is that which sits in between. And it has two parts. It has a control plane. So don't worry about what all of these acronyms mean, but the control plane primarily does things like registering users, authenticating users, setting up the security context. All of that stuff is done by the control plane. And whenever a session is set up for the user, the corresponding rules are installed in the data plane, and the data plane is actually responsible for transferring the data back and forth to and from the user. So this is a brief overview of the 5G core. So the next question comes up, what is so special about the 5G core as compared to the previous generation mobile packet cores, right? So the 5G core has a few special design principles that differentiate it. The first one is network function virtualization. That is, all of these components in the 5G core in the previous slide that I showed you are all being built as software network functions and not as custom hardware boxes. So this is a huge paradigm shift from the previous generation packet cores. And the reason this is happening is because the commodity hardware, network cards, all of these, and the software frameworks for IO, all of these are matured to a sufficient stage that we're able to get good performance in software as well, right? So we have network function virtualization. The other key feature is we have the service-based architecture. Like if you can see, the 5G core, the control plane is not one box, but many different entities, each of which are providing a different service, which are all communicating over REST-based APIs. So the earlier data center networks and all were designed in this microservice architecture, and telecom networks are also moving there because this is a good idea. And some of the other features are, this is all a cloud native design. There is a provision for fault tolerance, separate out compute from state. So again, these are all principles that the data center community has incorporated in the past, and the telecom community is also moving towards these principles. The other important feature is network slicing. You can actually have multiple slices of the network. Virtual networks can be provisioned over the same physical packet core, one for say high security applications and so on. And finally, there's also the provision of mobile edge computing. You can actually move the data plane closer to the base station so that the users can get very low latency and good performance. You can really take this core all the way to the edge. So these are some of the design principles of the 5G core. So now I'll quickly move on to some of the research we've been doing And these problems, I must say, have organically come up as we were building the 5G core for the 5G testbed project and optimizing it. These are some of the ideas that have come to us. So first, let us begin with the 5G core control plane, right? So this control plane has a bunch of entities which perform the control plane processing, like registering a user, handling mobility, setting up sessions, and so on. So all of these control plane entities communicate the other various transport protocols, for example, like STTP or UDP or HTTP over TCP and so on, right? So now the question comes up, if we are building, how should we go ahead and build the software, right? So one traditional design is to build all of these software simply over the Linux kernel's TCP/IP stack. So the Linux kernel supports communication over TCP, UDP, STTP, and it exposes a socket interface. So we can just build all of the 5G core components over the Linux kernel stack. And there are also various software frameworks available for HTTP, REST-based processing, and so on. But it is widely believed that the Linux network stack is not suitable to process at very high network speeds, right? It is not designed to absorb and process traffic at, say, a speed of 100 Gbps. Why is that? Because there are a lot of inefficiencies in the Linux kernel stack today. So I won't go into a lot of detail, but one example is you have data structures in the kernel, like the TCP control block, and these are shared amongst the multiple CPU cores of a machine. And whenever a TCP connection starts, it has to be processed. You have to acquire a lock on this TCP, and therefore the other cores cannot access the same TCP. So overall, there is a lot of inefficiencies in the Linux kernel stack. Anytime an application has to read data, you have to make a system call into the kernel, right? All of these transitions cause a lot of overheads when you're trying to build applications on top of the socket interface of the Linux kernel. And therefore, because of these overheads, these applications cannot scale to very high network speeds. Therefore, today, there are many alternatives being proposed, which are broadly called the kernel bypass techniques, right? For example, the most famous example is Intel's data plane development kit, or DPDK. With DPDK, you can simply bypass the Linux kernel, get all your packets into the application directly, into user space directly. Of course, some of the kernel's isolation properties are compromised, but once you have the packets, now you have bypassed the kernel's TCP/IP layer, so you can use your own network stacks to process user space network stacks to process these packets in user space, right? So prior work has really pushed these kernel bypass techniques. DPDK is quite popular, and they show a lot of improvement, but they're primarily looking at IO intensive network functions. That is where you read a packet and change some headers and send it out. But in the 5G core control plane, we have CPU intensive functions, which do things like authentication and all of that. So for such network functions, the research question we try to answer is the kernel bypass stack good or not? So we take a few components in the control plane of the 5G core, which are involved in registering a user, which is the user request comes over SCTP, then over HTTP, the request goes to other components, and authentication, key generation, all of this is performed. The packets go back and forth. And we tested out with multiple variants, for example, using short connections, using persistent connections. And we also, as you know, what short and persistent connections are is you keep the same TCP connection between components, or you re-establish it for every request. So we did all of these different options, and we also tried out many of the network stacks which bypass the Linux kernel that are available today as the state-of-the-art network stacks. And across all of these network stacks, so the key results, I won't go into a lot of detail, but the key results that we found is for this kind of workload that you see in the 5G core control plane, the Linux network stack is not all that bad, right? So for IO intensive workloads, when you are doing no authentication and things like that, the kernel bypass stacks was in fact much better than the Linux kernel. This is what the prior research has shown. But once you have CPU intensive workloads, once you read a packet, do a lot of computation on it, like in the 5G core, once you're doing so much computation, the small overheads involved in, traversing the Linux kernel stack do not become that significant, do not actually play such an important role. Therefore, the Linux kernel had slightly worse performance than the kernel bypass stacks, but it was not completely bad. And therefore, our conclusion from this research was that the Linux kernel stack is actually good enough, especially in like cloud environments where setting up these kernel bypass stacks can be a hassle or a security risk. In such cases, the Linux kernel is a good infrastructure platform on which the 5G control plane can be built. And the kernel bypass stacks are not very critical for performance. So then the next question came up as we were doing this research. So where is the performance overhead, right? What is happening? Why is how can we improve the performance? So it turns out that a key aspect of improving performance is a property known as multi-core scalability. That is, as I add more CPU cores, I should get more performance. Now, previous network functions that were considered by researchers, things like load balancers, for such network functions, multi-core scalability was easy. Why? Because network cards today are able to distribute packets to multiple cores based on the TCP IP headers. So one TCP connection goes to one CPU core, another connection goes to another core, and so on. And therefore, the load balancers can maintain state for each core locally, right? So all the state for this connection is here, this connection is here on different CPU cores, and you can avoid locking. But in 5G core, this does not work. Why? Because the state is not maintained at TCP flows. So until now, most of the research in the internet domain happened on TCP flow based network functions. But now in the 5G core, you maintain state at the granularity of a user. And the network cards are still distributing traffic based on TCP headers. Therefore, users' traffic can come on multiple TCP connections, can go to multiple cores, and therefore you will still need some kind of locking to access the user state, right? Because of this locking overhead is what is dominating. The kernel bypass overheads are not the bottleneck, but this locking overhead was what we found to be significant. And how do we eliminate this locking overhead? Somehow the network stack should know of user identifiers, should be able to parse the 5G specific headers, identify the user identifiers, and steer packets to cores based on these identifiers. And we implemented a small prototype which does that. And by doing this, you can actually have a lock-free operation because each user is localized to a particular core. The user state is maintained on a particular CPU core in a multi-core server, and you don't have to lock. And if you do that, we actually found that the performance significantly improves. If you can see at 24 cores, here is the locking based implementation and a lock-free implementation, and you're getting like 60% performance gains, right? So multi-core scalability is actually a very important property. If we have to build this packet cores software, we have to think about multi-core scalability. But the standards really do not give any thought to it. And splitting user traffic to different CPU cores inside the kernel, inside the TCP IP stack is actually very difficult. And we had to do a lot of workarounds to get this to happen. So the one feedback for future standards would be, can we improve the standards by thinking about things like multi-core scalability? So that is the first question that I would like to put out for us to consider. So next, moving on from the control plane to the data plane, right? So the 5G core or any packet core control plane is responsible for authenticating users and setting up sessions. And once you set up a session, the actual data transfer happens through the data plane. And the data plane is a component known as the user plane function or UPF in 5G. And there are a lot of expectations from this UPF. You should be able to forward traffic at a very high throughput, hundreds of Gbps with very low latency of a few milliseconds for applications like, augmented reality and virtual reality and so on. So this is the expectation in 5G. So what does the UPF do? The UPF is basically a packet processing entity, right? The user's IP packets come to the base station. They are put in some protocol specific headers, 5G specific headers called the GTP headers. So GTP is a tunneling protocol between the base stations through the 5G core, so that when the user moves, this tunnel also can move. So don't worry about what GTP is, but it is another protocol header that is added to packets, to data plane packets as they go through the 5G core. And once this header is, once the packet has to leave the 5G, the operator's network, this header is removed, right? So this UPF is primarily involved in reading these packets, processing these packets, adding and removing these headers. In the downlink, the header is added. In the uplink, the header is removed, and doing other things like counting the number of packets for rate limiting, billing, charging, QoS. All of these functionalities done by the UPF. But it is primarily an IO intensive packet processing entity, right? It is not doing fancy things like authentication or key generation like the control plane software. So what are the smart UPF implementations in the industry? Of course, previous to 5G, there was custom hardware. You got a hardware box that acted as the data plane. But now 5G onwards, because you have a softwareization of networks, so this UPF is being built as software, and most of the industry is using kernel bypass mechanisms like DPDK that I spoke to you about earlier. To get high work function, DPDK will give you huge performance gains over using the Linux kernel stack. And in addition to this kernel bypass based implementations, what you also have is something called programmable hardware. This is a new concept that is coming up today. So you can use the special hardware to accelerate these software components. So what is programmable hardware at a high level is, if you take a look at a switch or a router today, it is built, the silicon is baked to perform one functionality like forwarding Ethernet packets. But with programmable hardware, you can write code in a high level language called P4 and install it, using which your header parsing, your forwarding actions, the hardware's behavior itself can be customized from software, right? And you can use a software controller to actually change this behavior at runtime. So programmable hardware gives you the best of both worlds, which is fast data plane processing, the speed of hardware along with the flexibility of software. So a lot of industry players, the big companies are using these programmable hardwares to accelerate the UPF. So what we have done is, of course, these two ideas are out there, but there's no actual comparison of the cost and benefits of these ideas. So what we did as part of the testbed project is we built both these versions, one a pure software UPF on DPDK and one an accelerated version using a programmable hardware. We pushed the packet forwarding alone into the hardware, right? Still, the configuration of this hardware is still being done from software. The control plane messages to set up rules are still coming from software, are being done in software, but the forwarding of the packets is happening in hardware. So we built both these designs and we compared their performance, and we found that both of them saturate 40 Gbps, which is the network setup we have. But the offloaded version, of course, had lower latency than the pure software version as expected. And this is what the industry also says, oh, this hardware acceleration is good. But there is a catch here, which is, it is not just enough to forward traffic, right? You still have to configure these rules. When a user comes up, you have to set up these rules. You have to tear down the rules. All of that handling of the signaling messages from the control plane, that is still being done in software in all of the state-of-the-art UPF designs. So when you have a large amount of that signaling traffic, for example, like an IoT device, which sets up a session, sends a small 300 byte packet and tears down the session. When you have such type of traffic with a lot of signaling traffic also coming in such cases, this offload based design will not work, because this configuration of this hardware is actually happening from software, and that is still very slow. This path is very slow. Therefore, if you look at the control plane throughput of this UPF, it was actually much lower than the software version. So while industry says, oh, let's use hardware acceleration, it's not actually clear that straightforward that this actually leads to improved performance for all possible workloads. So what we are proposing, what we are working on in our research is how to process these signaling messages also in hardware, so that everything happens within the programmable hardware itself, and you're going to software for very little things like buffering and things like that, but most of the processing is happening in hardware. That is what we are working towards. But this is not easy, right? If we do this, we have a preliminary implementation, we see huge performance gains in the control plane performance also. And this design is actually very useful for workloads like IoT. But this is challenging because, once again, the standardization of these signaling messages is not done with this hardware acceleration in mind, right? For example, the various fields in the packet can come in any order, and parsing this in software is easy. But hardware works efficiently when there is a fixed order of all the information elements in a header. So we are running into issues like this, and we feel that if the standards are actually modified to enable to keeping this hardware acceleration in mind, we can actually get much better performance in the data plane of the mobile packet core. So to summarize, here are some of the ideas that we have come up with. So we took a standards compliant 5G core that we built in the 5G testbed project. We tried to improve its performance. And in the process, these are some of the issues that we found. For example, the standards are not very amenable to things like multi-core scalability or acceleration using programmable hardware. And if some of these things can be considered in the future versions of the mobile packet core, that will greatly improve performance. And the other thing that I didn't get much time to talk about is also around fault tolerance, right? So as I told you before, the 5G control plane is decomposed into multiple services that are tied together. And the split of services is actually not very amenable to fault tolerance. For example, if a failure happens, you want the user state to be stored somewhere safely so that even if a software entity, a server fails, you still don't lose the state of the user. But this state in the 5G core is split across multiple entities, right? Each piece of state, a user session state, is split across multiple entities. And therefore, you need many more complicated distributed systems protocols across these entities in order to safeguard the state. Even if one of them fails, the whole system comes down. So without going into a lot of detail, this was not designed with fault tolerance in mind, right? And so we can also think about a better decomposition of these services in the 5G control plane, keeping in mind things like fault tolerance, right? So in summary, things like performance, multi-core scalability, fault tolerance, these are also important. It's not just enough to have a software version of the 5G core. Think about these things. And when you think about these things, the standards can really improve to enable these things in our implementations. So that is all I have right now. And I would like to thank all my collaborators and students who made all of this research possible. And I'll be happy to take questions if there is time.
Thank you, Mythili. Thanks. Wonderful talk about, how standards play a role in the performance of the core network. At the very fine level. I think it's very apt to say that. Once you start implementing all this, you'll start understanding how small things like the header, how the bytes in the headers play a role in the throughput of the entire system. Very, very, very fascinating. So, Mythili, I think if there are any questions, I will send you on the chat so that you can answer.
Yeah, sure.
Thank you. Thanks a lot.
I'll be happy to. Thanks a lot.